So you probably see it gets pretty messy at this third level. I was very careful to keep all my decimals, and here's the linearization that I came up with. Zoom in if you need to. And then when I set that equation equal to 0 to find the root of this third tangent line, I came up with an x value of 2.7619. And going back to the graph, you can see the idea here was there's our first tangent line, and then we took the x value of the first tangent line, and I'm going to zoom in so you can see. We took that x value and went back up to find a point on the original function that had that x value, and that was this point right here. And then we found the tangent line from that line, and we found the intercept of that tangent line, and then we went up to the function and we found the point that had the same x value as that intercept. And then using that point, and I'm zooming in again so you can see, we found a third tangent line, which was this one. You can see the equation. And you can see the third tangent line really is so close to the function that I can't distinguish between the intercept of the tangent line and the true intercept of the red function. Of course, if I zoom in far enough, they're not exactly the same, but they look really incredibly close. This number that we found was on the tangent line, if I can get it here. That's the number we found, 2.761. There it is. And it's very, very, very close to the true root, which I know because I have technology. I can find the true root, which is this second one right here, 2.7639. And ultimately, this is now a judgment call. Do you choose to do another round of this and get even closer? If you did, you would get closer. For this problem, we'll stop there. And we'll just finally write as our conclusion, we've estimated, looking at all the work we've done here, we've estimated what we think the root's going to be. And we can go ahead and say that we're guessing f of x will have a root at approximately 2.761. Now there's good news. And the good news is also courtesy of Mr. Isaac Newton. And the good news is that there is slightly a shortcut. Have you noticed that the work that we did in the second two columns was always kind of the same? And I've zoomed way out so you can see this. You may not see the actual numbers, but we always found the number, we plugged it into the original function, the derivative, and then we found an equation that looked exactly the same because it's all point slope form. And then we always distributed and always divided. And then even the solving, we always subtracted or added the constant and divided. So those two steps, if you think about it, can be kind of combined into a formula. And there is a formula if you want to memorize it. You don't have to, you can just do the whole process out. But if you want to memorize it, there's a formula for how you use the last x value to find the next x value. Here's how you derive the formula. In each row, we started out with point slope form, and we plugged in three numbers. The number from the original function when you plug in your x value, the derivative function when you plug in your x value, and the actual x value. And then after setting up point slope form, we isolated for y in each of these examples. So I've done the same thing, leaving all the symbols in. Notice here that this is a true x, whereas all the things in blue represent numbers, numbers that depend on whatever our original x value was that we plugged in to the function and the derivative. Those would be in these positions. From here, the last step was to find the root. In other words, we replace y with 0, and again, isolate the true x. I can do that with symbols. It looks like this. And you don't need to write down or study this math, but you should understand basically what I'm doing. There I set it equal to 0, just like I did with numbers right here. At this step right here, I moved these two terms over to the left, just like I moved 3.2 over to the left. And then I divided both sides by the coefficient of x, which is the derivative right there, just like I divided by negative 1.2. And when I algebraically simplify this, those terms cancel, and the expression I'm left with is x sub I minus f of x sub I over f prime of x sub I. Think about what these symbols mean, and this is the shortcut. You're going to need to memorize it, and you won't memorize it just by looking at the symbols, but if you understand what they stand for, this will be really easy. What does x sub I mean? Exactly, it's the previous estimate. So the first guess we made was 0. That would have been x sub I. Then what does f of x sub I mean? This means plug in the previous estimate to the original function and put it on the top of the fraction. And then how about this one? This means plug in the previous estimate to the derivative function and put that number on the bottom of the fraction. Then when you simplify this and you actually divide those and subtract, the whole thing is going to equal to x. What is x going to be? Right, it's the new estimate. And then you start the whole process over again. So this formula basically simplifies all of the algebra you were doing in these two columns into one step. Of course, you still have to plug in the x value to the original function and the derivative, which is what we did first of all. And then you use those two numbers to basically go directly to that number there. Then you take that number and you start it all over again. Let's try this. We'll do this with another example. So back to where we were in the lecture. We just did Newton's method. It was a way to find the root. We did. It was a number close to 2.761. And the reason we had to use this method, which involved a bunch of tangent lines, is because we couldn't solve this equation algebraically. At the end of that example, we realized that there was a shortcut formula for finding closer and closer x values. So let's do another example using that shortcut. I think you're going to like it a lot better. Here's a new function, and here's a graph. Go ahead and get set up, find the derivative of this function, and then set up your table. Right, so the derivative is just a chain rule, and remember the derivative of ln of something is 1 over something. And last time we set up our table with 3 columns. But the beauty of the shortcut, which I'm about to show you, is that actually we can simplify these 2 steps into one step. And the one step is to find the new x value. We start with a guess, and then we do something to come up with a new guess. And then we start all over again with the new guess. In order to find the new x value, we're going to follow that formula, remember? The original x value minus the original y value divided by the slope of the original point. Let's try this. Let's look at this graph. Now, this actually isn't exactly the perfect graph. This is just an estimate of what the natural log function looks like, because realistically, when you do this, you aren't going to know what the functions are. So this is an estimate of the shape. If we think about it, we expect the root to be somewhere around 1. In this case, it looks like it's a little below 1. So maybe we should start by guessing 0.5. Using that guess, what's the first thing I need to find? Exactly, I need to plug in that number, 0.5, into the original function and the derivative function, so I can use the answers in this formula. So the best way to do this is in your calculator. Put g of x into y1 and g prime of x into y2. Should look like this. Pause if you need to get your calculator out. And again, I'm just trying to find a quick way to plug these decimals into these messy formulas. The calculator will do it for you both at once, actually. If you set the table to ask, it doesn't matter what the start and delta table are, but if it's asking you and automatically giving the dependent variable, when you go table, you can plug in 0.5 here into these 2 equations. And then we get this really annoying error message. What this error message means, and this could happen to you, is that 0.5 is actually not a valid input for our function. You could actually even look at this and see why it won't work. If that happens, it just means that our first guess was no good, and we need to start with a different first guess. Let's try 1.5 instead. Just like before, I need to plug it into f and f prime to get out those numbers that I'll then use in this formula. Using the calculator to plug in 1.5, 1.5 gives me a perfectly fine value, both for the y value and for the derivative value. So to find the second x value, I take the original x value and I subtract the output of the original function divided by the derivative at that point. I evaluate this in my calculator, and just like that, I have a new x value to try. What am I going to do next with this x value? Exactly. I'm going to use that as the next x value and repeat the process. And this is where having the equations in your calculator is really convenient, because I can go back to the table without adjusting anything, and all I have to do is type in 1.6078, and I get my two new y values and derivative values. Once I have those two numbers, how do I find x3, the third guess? Right. Plug into the formula, original x value or last x value minus last y value divided by last derivative value. And then we get a new x value. What do we do with this? Exactly, we repeat the process and we find a fourth estimate. Now, notice that these estimates are pretty close to each other, but they're not necessarily going in the same direction. They're not always getting bigger. For example, here it went from 1.6 to 1.7 back down to 1.6. So you are guaranteed that you are getting closer and closer to the actual root. You're not guaranteed that you're always going to increase. It could jump back and forth on either side of the true root. Go ahead and find one more. Use x of 4 right here and find one more approximation. What do you get? When I tried it, I got 1.6180. And so we can see we are eventually getting to a point where we have the same decimal and hundredths place. And so that's a pretty good indication that you've truly found the root. Ultimately, it's a judgment call, how many iterations you choose to do until you decide you're really close enough. Just for fun, I can show you Desmos, what this function actually looks like. Looks like this. And the true root, according to Desmo, is 1.618, which is just what you just found. So cool. All right, last thing you need to know, and then we'll call it a night, is there are times when Newton's method might give you a problem. Look at these two graphs, see if you can think about how they connect to Newton's method, and see if you can guess what the two problems are. Right, so most of you probably see the problem with this. If you pick an x value as your first guess that happens to have a tangent slope that's 0, your tangent line is never going to touch the x-axis, so you're never going to come up with another x value. That's kind of what happened to us when we made that first bad guess. Technically, ours was a vertical tangent where it didn't exist, but that's why we ran into problems. In cases where you make a bad guess as your first guess, you really just have to guess again. Similarly, on the left-hand side, the problem here isn't that it didn't work. This person was looking to figure out what decimal this number is right here. So they made a guess of 4 or something like that, something close to 4. They found the first tangent line, and then looking at where the tangent line has an intercept, we use that as a new x value, and we come down to the function and we find the new tangent line, which is the blue one. And then we found where the blue line intersects, which is right here, and we go up back to the original function and find a third tangent line. And the third tangent line's intercept is so close to the original function that we stopped there. We ended up with a root. The problem is we ended up with the wrong root. So in cases where your function has more than one solution, you may have to make a couple guesses. If we had started like right here, for example, we probably would have ended up with the correct root. This has been Newton's method. You should remember who Newton is. You should remember why we use Newton's method. What kinds of problems do they solve? You should remember the idea of using tangent lines to get closer and closer and closer to a true x value. The process you don't have to be perfect on. We'll practice more in class. Have a good night.